Thank you. The picture here is the Reykjanes power plant. I will talk about maintenance. How does it work?
The green button.
The green button doesn't work.
You may have to blink like a few times.
Oh, okay. I will show you some schematic diagrams of the power plants, and I will go over the maintenance quantity and the origin of the usual breakdowns and problems, and show you how we organize a power plant with staff, and what systems we are using, the DMM, and we use KKS coding of assets. And finally, I will talk a little about geothermal systems operability. This is an aerial view of the Svartsengi power plant. It was built in several stages. Is this a pointer?
Yes.
It doesn't point. There is no point in the pointer. Okay. As you see, there are many buildings, and the plant was built in several stages, starting in 1976, and the last part was added in the year 2007, plant number 6. What you also see is our spin-offs, the Blue Lagoon and the Blue Lagoon facilities. This is a simplified diagram of the Svartsengi power plant. Oh, sorry. We start, to your left is the geothermal wells. We start with the wells. We go through separators and pipelines and moisture separators, not shown, to turbines, to heat exchangers, to binary organic rankine systems, and cooling towers, and re-injection. So it's quite complicated, and we are not quite sure of a new operator until after 2 years of work that he should know everything about the plant. Reykjanes power plant is far simpler. There is just a one line through the whole system. There are several geothermal wells. There is only one separator for each 50 megawatt unit. There is one steam line. There is one moisture separator, and one condenser, of course. So we try to keep it as simple as possible, as opposed to the Svartsengi power plant. The main troublemakers, so to speak, are the geothermal fluid. It is something we cannot control. Our geothermal fluids have a salinity of 66 to 100% of seawater. And what happens in salty water is that all chemical reactions are a lot faster, especially silica scaling. We have geothermal gases from 0.7 to 2%, maybe some wells over 2% gas. 96 to 98% is carbon dioxide, and most of the rest is hydrogen sulfide. Carbon dioxide is not harmful unless it's only compound dioxide and no oxygen. You understand that? But the hydrogen sulfide can be dangerous in high concentrations. The steam condensate can have a very low pH and can be very corrosive. Our fresh water, because we are producing district heating water from fresh water. Our fresh water has 300 microsiemens per centimeter conductivity and 70 ppm chloride. It is actually very low, far below all drinking water standards, but it's only the chlorine content is 10 times that of the Reykjavik system has. So it can be tricky when heated or when we have some leaks somewhere. This district heating water can also develop scales from magnesium silicate, especially if temperature is over 100 degrees and the pH is larger than 8.9. What we do actually in our power plant, we control the pH by adding some carbon dioxide, lowering the pH to acceptable levels. This is a list of assets, as Guðmundur was showing us. And we have 44 geothermal wells, 8 separators, 7 moisture separators, 4 condensing steam turbines, 7 Ormat organic Rankine cycles. We have 1 back pressure turbine. We have 5 re-injection wells. We have 36 cooling fans. We have 70 control valves. We have hundreds plus pumps. We have 30 kilometers pipelines. We have thousands of valves, 100 or more steam traps, 25 heat exchangers, 20 control systems. We have 1 SCADA system, fortunately for the whole plant. We have 30 over 30 flow meters. We have at least 80 high voltage breakers. We have 5 high voltage protection systems. We have 11 hydrogen sulfide air cleaning units and 6 flushing brine silencers. And there are many things I have not presented. It's much more complicated than that. This is a separator in Reykjanes plant. This is a steam ejector system to make the draw out the non-condensable gases from condensers. This is Ormat organic Rankine cycle unit. Actually, we are proud to have the oldest working Ormat units in our power plant. So we are pretty proud of our maintenance system. This is how complicated it can get, the power plant 6 in Svartsengi, which has several inlets and outlets, just to get it complicated. Oh, okay, of course, to get most efficiency as possible. This is a turbine rotor from the same unit, showing the turbine blades and all kinds of labyrinth shaft seals. We have here a steam trap and a mist eliminator for getting the stuff out of the steam before it enters the turbine. We have steam turbine blades, actually only this size, so it's a big picture with iron sulfide scaling. And we have erosion in a turbine casing because of wet steam. We have a surface condenser, outside and inside, and silencers, which are our own design. Silencer for flushing brine. Of course, and as I said, the roots are in chemistry, start and end in chemistry. We have various kinds of corrosion. We must be careful of thermal shocks, and we have a lot of scaling. This picture showing metal sulfide scaling in a pipe from well 11 on Reykjanes. Our mitigation was enlarge the pipe from 14-inch to 20-inch and install openings to be able to clean out the scaling with hydroblasting. This can happen to a mist eliminator. This particular was made of 316 stainless steel. We changed over to duplex stainless steel. It lasts many, many years. This is a crack in a steel pipe. You can see the crack. Yes, it's quite obvious from the left to right and from the center and up. This is because we were not careful enough in choosing our steam pipes, material for steam pipes, and to not having the proper heat treatment. Hydrogen sulfide corrodes electronical equipment made of copper and silver and things like that. And what we must do is to have all electrical or electronic equipment in compartments where the air has been cleaned and H2S filtered. In the pipelines, we must be careful of choosing the right material. We use seamless carbon steel pipes for steam lines and wellheads. Ordinary welded steel pipes can be used for brine and two-phase flow pipelines. Titanium has to be used for plate heat exchangers and seawater condenser tube, that is, a condenser that are cooled with seawater. Condensate pipes are made of 316 stainless steel, and tube heat exchangers for district heating water are usually made of duplex stainless steels. Our maintenance staff, the permanent staff, is about 30. And what is special in our plant is that the operators, who are marine engineers, they do both the operation and maintenance, and they work 1 week on operation, 1 week on maintenance. So they all of them knows, all the plant knows all what is going on. We strive to use reliability-centered maintenance and do necessary condition and monitoring. And what is quite essential is good education and training. And when we have a major modification and workovers, we hire in contractors. Usually we have a few contractors working on site in addition to our own people. And what is very important is to keep the power plant clean. Then it's much more easier to detect leaks and other faults. We use various special tools, and we use KKS or Kraftwerk Kennzeichnung system for the coding of all assets, and we use the DMM maintenance system as Guðmundur was presenting. And we use it for our logging equipment inventory. We use it for making work orders. We keep all our manuals there, and we do maintenance reports, and we use it for quality control. And this is one of the main bases for our ISO 9001 accreditation. I want to talk a little about the geothermal system. This is the foundation for everything. We have been lucky operating the, lucky or wise. I'm not quite sure. It looks very wise how we have operated the system, at least now, after 40 years of operation. So we have had a gradual pressure drawdown through the years. In recent years, our principle has been that we must have a little pressure drawdown, but not much, and this is to keep our two-phase part of the system, or the steam part, growing a bit larger, but we must also keep up the temperature, so the reinjection must not be too intense. We see actually the hill in the drawdown. It was because of a leak from an uncased part of our reinjection well. So we had an extra reinjection from the groundwater system into the geothermal system. But that was cased off and the problem solved. And on the diagram here to the right is the pressure measurements through many years in monitoring well number 12 in Svartsengi. You can see that the pressure in the liquid part is going down gradually, but because we have managed to keep the temperature constant in the boiling zone and in the reservoir, we get higher wellhead pressure. Problems when you do it the other way around, when you re-inject too much, you get higher pressure in the water-dominated part of the reservoir, but that means you get lower wellhead pressure. And if not careful, you can, with re-injection or overproducing the field, you can maybe have the pressure drop at the wellhead so severe that wells will not be, you cannot use the wells. But we have been very happy and very lucky. So we are very lucky, so we are very happy. With our wells in Svartsengi, we have many wells which are 37, 8 years old, still working and going strong with almost same, well, not quite the same, but almost the same output as in the beginning. So because of this, we have of this drawdown and the growing steam zone or two-phase zone, we have increased the enthalpy and especially the exergy. The exergy is part of the physical number for how much power it can produce. So that is the most important part of operating a geothermal reservoir is not losing the exergy of the system. It has increased about 55% from beginning, while the average enthalpy has only increased just over 35%. So my final word to geothermal systems operators: preserve the boiling zone in your reservoir. Thank you.